Good day, everybody. Today we're going to look at interpreting a system, interpreting spring problems as systems. So general spring differential equations. Here we have your equilibrium where the mass would rest. So here's an example, just throwing some numbers without units in an initial condition. This would correspond to an initial displacement of 1 unit, which we'll say is downwards for the positive direction, and then releasing with no push, so initial velocity of 0. We'll go through the work of solving that, but this would be the solution because it's underdamped, so that would be the decay. I wanted to write it as a system. I like to use x1 as x and x2 as x prime, and if you solve, this would be the system. Here it is in matrix form. Do have an initial condition. So let's look at the plot. I have that one right here. This is a plot of the system. So remember, the horizontal axis is the displacement from equilibrium. So our initial displacement was 1 unit away downwards with no velocity. Velocity is this vertical axis. So then it starts heading upwards, but that's the upwards is the negative direction, so the velocity is negative. And then you gradually reach you go past the original equilibrium, you go beyond it because you have positive you have a speed in the up direction, which is negative velocity. Then you reach a maximum height above equilibrium, which is our negative direction. And then after it has its maximum height above equilibrium in the negative direction, it starts heading downwards. Downwards is the positive direction, so the velocity is positive. And it again reaches its maximum displacement in the positive direction when the velocity is 0. And then it's going to head back up with negative velocity and so forth. So you can interpret that way. Notice a few things. If it's undamped, you reach your maximum speed as you cross the equilibrium. But with damping, you're going to reach your maximum speed right here, negative velocity, before. So that's kind of where the spring force and the damping force match. In fact, at these points are where the velocity is 0. So the velocity is 0 over and over, but not at equilibrium because there's damping. From our solution, we see we have a frequency of root 15 over 4. So the period will be 2 pi divided by that, and 2 pi divided by this frequency will be 8 pi divided by root 15, which I put here. So here's 8 pi divided by root 15, so that'll be our period. So we'll go from maximum positive peak to maximum positive peak in that amount of time. Half of that is this value. So we'll go from positive peak to negative peak in that amount of time, and then from negative peak to positive peak in that amount of time. And then half of that would be this value, which will be not where we reach the equilibrium, so we'll see that. And I'm going to plot, so I'm going to put time in to the equation. So right now what we see is, with this plot, position and velocity. So I can look at any point on the plot and I can say, oh, if my position is this, my velocity is that, right? So if my position is, say, negative 0.4, my velocity is maybe negative 0.3, something like that. But we lose time, but we can put time in if I animate it. So I'll put that in, and we'll see the time up here in this top. Right now it's at 0. And so there it goes. Let's do it a little more slowly. So here we are at t equals 0 or 1 unit below equilibrium in the positive direction with no velocity. So you see that in the vertical, the velocity is 0, and then the positions given by the horizontal. And now if I increment time, each of these is 1 over 32nd of the period. So there's 1 step, 2 steps, 3 steps, 4 steps, 5 steps, 6 steps, 7 steps, 8. So that takes me to 1/4 of the period, that 1.6223. And I have not reached equilibrium at 1/4 of the period. Again, if there was no damping, you would. And now I'll do 8 more steps, but I'll reach the maximum position in the negative direction. So 1, 2, 3, 4, 5, 6, 7, 8. So now the total time's that 3.2446. So that's half the period. So you go from peak to peak in half the period, positive peak to negative peak, or vice versa in half the period. Now to go back to the positive peak, again, if I do 1/4 of the period, 1, 2, 3, 4, 5, 6, 7, 8. It's a little hard to tell, but so 4.8669. So that's the sum of the half and the 1/4. And we have not yet reached equilibrium again. But if I go 1 more 1/4 period, I will reach the other peak. Oops, I lost track, but there we are. So again, so that's how we can interpret this graph. Horizontal is displacement, vertical is velocity. Time is in there, you don't generally see it, so we're looking at called a phase portrait. So that's the main idea. I do have a few other examples to blast through a little quicker. So again, with the spring, with these values, leave off units, and now I just put in an initial displacement of 0.7, initial velocity of 2. This one came out to be critically damped, and the solution was this. As a system, again, if x1, I like to call x or whatever, and x2, x prime, and if you solve, well, take the derivatives, x1 prime is x prime, but that was defined as x2. x2 prime is x double prime, and if you solve for x double prime right here, it would be this, but x and x prime, we know are x1 and x2, so you get the system. So this graph represents this solution. So again, we've got our initial velocity of 2 and our initial displacement of 0.7. So the mass does go a little beyond 0.7. It slows down really fast though. So if you pull it down and then push it down, it goes down farther, but it slows down really fast. It reaches its maximum displacement downwards, and the velocity is 0 there, and now it's going to head up and kind of slowly, basically, head back to the origin. The graph would look like this. So this is critically damped. I might say something later. I'm going to change the initial velocity to, instead of pushing it away from equilibrium, to push it towards equilibrium, the same speed of 2, but so instead of being positive 2, it would be negative 2 for the velocity. So everything else would be the same. But I want to do that when I look at overdamped. So again, this one, I have it so that I can easily go to overdamped. I'll keep the initial conditions the same and K and M the same. I'm just going to change the damping constant from 1.2 to 1.3. So here we are, and then this would be the solution. Now it's overdamped. Again, as a system, I just want to look at the graph. So it's pretty similar. Start with initial velocity of 2 and initial position of 0.7. You push it downwards in the positive direction, so it does go beyond the 0.7, and then reaches its maximum displacement down, velocity is 0, then heads back up and heads to the origin. So this is overdamped as opposed to critically damped. If I look at the two solutions, so this isn't for the system's way of thinking, but the overdamped in black, in the end it decays faster. It goes under the overdamped. Everything else was the same. K and M were the same. Initial conditions were the same. Now I will look at changing the velocity to -2. So then I start with a velocity of -2 and position of 0.7. It goes actually beyond equilibrium. So it's going to have some negative x with this velocity and then head back towards the origin. So it's going to overshoot the equilibrium. But just once. You can actually prove you can only cross equilibrium at most once if you're overdamped or critically damped. Here we're critically damped. So this would be the graph. So we did pass the equilibrium once, which is the most you can do if it's critically or overdamped, and head back. And then here's for the overdamped, starting at -2 for the velocity, 0.7 for the position. So similar, you pushed it towards the equilibrium so hard that it went past equilibrium and then came back. And this is the solution for this overdamped. So getting past equilibrium. If I put the critically damped and overdamped together, critically damped will always hit the equilibrium or reach equilibrium sooner than the critically damped for the same M and K and initial conditions. And then it also goes back under the overdamped. If I zoom in, so I will zoom in on this part of the graph, and the critically damped goes under the overdamped. So the critically damped crossed equilibrium sooner and then goes back under as well. So there they both are again. I'll now compare a undamped spring with a pendulum. So again, if I make the damping constant 0, I get this. And then the solution, we're going to kind of vary the initial position and velocity, but just sines and cosines. So now there's no damping, so there's no exponential decay. As a system, again, x1's x, x2's x prime. It would look like that. And where's the matrix form? So let's look at the plot. This first one has the initial conditions of 0.5 for the displacement, 2 for the initial velocity. So I'm roughly starting right here on the curve, and then so you pushed it in the positive direction, so it reaches its max displacement at 0 velocities when you change from increasing to decreasing. So yeah, your maximum displacement's there, but now your maximum speed's at the equilibrium. So that wasn't the case with damped. And you don't lose any energy, so you essentially just go up and down forever in this idealized solution. So now I will compare this to the pendulum. So instead of x being the displacement of the spring from equilibrium, our variable, I'll go ahead and call it theta, will be the angle that the pendulum is at. And then it ends up solving this differential equation, which is nonlinear. So you're not going to be able to solve it. Sometimes they do the approximation of sine theta is approximately theta. And then, well, if you assume sine theta is roughly theta, and that's good for small thetas, then you actually get the same differential equation. Yeah, right there. So as a system, I'm just going to let x1 be theta, x2 be theta prime. So that's kind of like the angular velocity and the angle. And you wouldn't be able to write this one as a matrix because it's not times, it's composed into a function. So you can't write this one as a matrix. But you can still write it as a system. x1 prime is x2. Oh, yeah, I got it here. And x2 prime is -10 sine of x1. Again, which is, for a good approximation, -10 x1. if x1 is small. So I've got a couple of plots here. The one we're looking at is for the angle of 1.2 and which is almost 70 degrees, so that's a really big angle for a pendulum. So 1.2, you know, beyond 1 for the initial angle displacement, and I just release it. So no initial push in either direction, and then it'll swing back and forth. So it swings to equilibrium, so it crosses equilibrium with its maximum speed here at 0, and then goes back up to its most negative angle. So once it crosses equilibrium and continues, well, from my point of view, that way, I'll call that, you know, negative angle. So when the pendulum's down, that's 0, and I called to the right positive, to the left would be negative. Right, so the pendulum's swung to the right, then swung to the left, maximum, reaches 0 velocity, and then it swings back, so it's heading back to equilibrium, so its angular speed is positive because the angle's increasing from its most negative to less negative to 0 to positive. So the angular velocity is positive until you reach its most positive angle, and then it hits 0 and then heads back again. So going round and round is the pendulum swinging back and forth. Most to the right with 0 at equilibrium, most to the left with 0 velocity, then heads back, crosses equilibrium on the way to the most positive with its most positive velocity, and so on. Right here, above this, is the plot of the initial angle is -3. So if you picture the pendulum, should probably get one, but if you move the angle all the way to pi/2, it'd be a right angle with equilibrium. But keep going, and if you went all the way to -pi, you'd be straight up. But I didn't quite reach -pi, right? So from equilibrium, I will move to my left, maybe for you that way, but I'll just go this way again. Pi/2, keep going, not quite to straight up, which would be -pi, but almost. So to -3 in radians for the angle, but then I gave it a push in the positive direction. So I didn't push in the negative direction, go the other way, but push in the positive direction. So it's going to come back, but, well, let's see. So the initial angle was -3, and the initial velocity was +3. So you push it, so it goes, and it's in the positive direction. It's just getting faster and faster until it reaches equilibrium, and then it goes past equilibrium, but now it's in the positive angle, and it still has positive angular velocity. And right here, it's going to reach, you know, 3, the angle of 3 with velocity 3. There's no energy lost in this case. But so once it went around, and now it's at angle 3 with angular velocity 3, that's enough to have it keep going. So then it just goes over. Again, this is an kind of idealized pendulum that can swing around and around. So if that were the case, you know, there's no mechanics that would stop it. So it went beyond equilibrium. So it's actually going to always have positive angular velocity. So the angle, if you go beyond 2 pi, right, you know, it'll go beyond pi. And so essentially the pendulum is just going to go round and round, not back and forth, but round and round. And I didn't continue the graph here, but that's what this graph would be right here. So it's going to go round and round forever with no energy loss, and always with a positive angular velocity that changes, but from whatever its min is, just a little below 3, I would guess, to its max. But that'll be enough to keep going. And so as it goes round and round, you say, well, the angle was -3 to 0 to pi over 2, pi, 3 pi over 2, 2 pi, and so on. So the angle just keeps going beyond 2 pi, 5 pi over 2, 3 pi. So that's what this would represent. Here's the small angle approximation. Although it's not that small an angle, the initial angle is 1.2. But if I put that here, so this would be, if you say sine theta is theta, which is kind of like the spring differential equation. And if I overlap the two, ignore this one, but you can see the sine theta is theta isn't too bad. I mean, but it was a really big angle. If I make the initial angle much smaller, well, I'm not going to go too small though, because with the naked eye we can't see too much. I'll try 0.8. So 0.8, so that'd be like 45 degrees. So 0.8 in radians. So, and here's the pendulum, and here's the small angle approximation with 45 degrees. So let's put the two together, and there they are. So you can kind of see the difference, but not really. Here they are. So in blue is the sine theta equals theta approximation, and in black is without that approximation. So notice the blue is a little beyond, and if we were to compare the periods, the period of the pendulum would be more because it has slower speed. The small angle approximation reaches bigger speeds, so it's going to have a smaller period. If I make the angle 0.1, well, it's really small there, but I can put them both together right here, and well, you can't really see the difference between the two. So the small angle approximation works really well. 0.1 radians is less than 6 degrees. And even most pendulum clocks, I think, go more like 3 degrees, so even half that. So they are both graphed here. Lastly, I'll look at some forcing problems. Maybe I'll do two at once here. So no damping, but with forcing that's similar to the resonance, but not the resonance, and then one that is the resonance. Our initial position and velocity would be 0. So if there were no forcing, we'd just stay at equilibrium. We're back to a spring problem. So the spring at equilibrium with no, if it's at equilibrium with no velocity, it's going to stay that way, but here there's forcing, so that'll force it to move. So this is the actual solution, and we're roughly at 20 pi right there. We've got this little beat phenomena. So there's the differential equation. And what I will first look at is I'm going to go to 10 pi, right? So if this is 20 pi, first I'm going to go to 10 pi, which is where I'll reach my maximum peak, and then you come back in. So let's see if we can see that. So here's the system. So we start at 0, 0, and you go out. I mean, the position and velocity, they're not equal scales, but I kind of have a scale, so it looks circular. But at 10 pi, so t goes from 0 pi to 10 pi. So in other words, 0 to 10 pi. So we reach kind of our maximum peak, and then if I go to 20 pi, I'm going to cycle back in. So we cycled back in and reached kind of 0, 0 again, and then we'll cycle back out if I were to repeat. I've got this here, so if I change it to 10 pi, then it's still the same graph. I'm starting at 0, 0, but I'm only looking at that part of the graph from 10 pi to 20 pi. So in other words, I start here, and now we're spiraling in. So it's almost the reverse of the spiral out, but it was a little shifted, so we could see the difference. And last look, go from 0 to 10 pi, our maximum, so there's spiraling out, and then go to 20 pi, so spiral out and spiral in. And then it would repeat, so it gets messier. So here it is to 40 pi, but it's just kind of going over the same thing. And then with resonance, this will be the solution, which pictorially is like this. So with resonance, your amplitude grows. Right, here's the solution, 4t over 5 times sine. So it's a sine wave that's kind of expanding as time goes on. Don't know why the direction field didn't get plot, but it does plot the solution. So we're going to start at the origin, and it's just going to grow and grow and grow. So it's not going to spiral back. I go to 20. I mean, you can see it's kind of equally spaced, and I mean, because it's growing linearly in its position. Right, 4t over 5, right? So it kind of grows linearly. And last one to look at, forcing with damping. Again, we'll start at equilibrium, so we'd stay there except for the forcing, and then you get a solution, kind of a particular solution with no exponential decay, and you get a complementary solution to make you fit the initial conditions, but it has exponential decay, sometimes called the transient solution, and steady periodic. So you can write it as a system again, and you can even do it as a matrix if you like. The solution would look like this, or here it is again in black, as the sum of the steady periodic or particular solution and the transient solution, the complementary solution that had decay. So the black is the sum of that blue and red, but the red decays, so essentially the black looks like the blue. Here it is as a system. So we start at the origin, but then there's forcing, and we kind of peaked a little bit. We reached a maximum a little bit more, I think, in the negative direction. If you zoom in, you can tell that. This is the velocity. It's kind of weird. But gradually you go to the steady periodic, so that would be just going round and round, which, based on my dimensions this way, looks circular, but the main thing is you can just kind of orbit at that point. So you the forcing will mean you have kind of the same amplitude. All right, so that's interpreting a phase plot and using systems to convert second order into a system, which again, if you can plot, then maybe you can gain some information. So all of these, I did find the solutions to, but there's some, like the pendulum, you can't really get analytically. So it's nice to have phase plots, although here you don't see the direction fields, but on these others, hopefully you can interpret horizontal for position, vertical for velocity, or sometimes angle and then angular velocity. But all right, so hope that made sense. Thank you and have a good day.